Okay, I think this is the absolute worst lesson in the entire unit. And it's not too bad once you kind of do it, but when you first see it, it just looks miserable. Okay, so if we want to have our function approximated, we can take our approximating polynomial, which of course terminates, and the remainder. So if I take whatever's left over and add it to what we use as an approximation, that's our real value. For example, if I was approximating e to the x, and I decided to only use this in my approximation, this would be my approximating polynomial, which would actually be a P1 Taylor polynomial, and all of this would be the error, or the remainder. Now, what we want to do is see what this remainder is. Now, what we had done in a previous section is I said, oh, the error, which is the remainder, is the real value minus the exact value. Well, we wouldn't be building Taylor polynomials if we knew what the exact value was. So we need to have an idea of how bad our polynomials are, how far off from where they are exact, or from the real value, but not knowing the real value. So we've got to get some bound on the error. All right, so kind of the picture here is you have your real function right here. Here's your f of x. And our polynomial is going to be exact where it's centered. And this right here, where we approximate, is going to be the remainder, or the error. And the error is always positive. It's going to be the actual value minus the estimate value, or f of a minus the approximating polynomial. So again, looking at this, if we took all of this for our approximating polynomial, this is what's left over, the remainder. So what we want to do is maximize the remainder. How we do that? You see right here, this was the nth derivative. That's as far as we went for our Taylor polynomial. So our remainder is going to be the next term. So the next term would be the n plus 1 derivative, x minus c to the n plus 1 over n plus 1 factorial. What we want to do is maximize this. So we want to see how big this possibly could get between where you're centered and where you evaluated your function. AP will always give you a graph or a value to use. We do one or two problems where they don't give you that, just so we can practice it. Now, if this was an alternating series, we don't need to use Lagrange error. So for example, if I had sine x and my polynomial was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. If I use x cubed polynomial as my approximation, so maybe I say sine of 0.1 cubed, this term right here would be the error in the approximation. So I would plug 0.1 into there. Because remember, for an alternating series, just looking at a different alternating series, the error is no more than the first omitted term. So if I use this, my error is less than 1/4. Now think about that. It's an alternating series. So we subtracted 1/4, then we added 1/5 back. Then we subtract 1/6. So we keep adding and subtracting smaller amounts. So it's going to be no bigger than that first omitted term. So we do not need to use the Lagrange error if it's alternating. Okay, so here I give you an example of a Taylor polynomial. Who knows where it came from? I just gave you some values. So the first thing we do is plug them in. And I want you to find the value at f of 3.2. So we plug that in. Now we want to talk about the Lagrange error. This is our approximate. So since that's a 3rd degree Taylor polynomial, our Lagrange error is going to go to the 4th degree. So what would the 4th degree look like? It would have the 4th derivative, the 4th power over 4 factorial. This right here is always whatever's right there. That's going to go right there. So what we need to do is maximize this derivative. How big is that derivative? Well, we told you that the derivative is less than 35. So that's what we put right here. Over 4 factorial, because that's over 4 factorial. So all you're doing is looking at the next derivative. And what that means, if the real value is going to be the approximate minus the error, or plus the error, I'm sorry, and the approximate minus the error. So it's going to be somewhere in between there. So I know if I use my Taylor polynomial to approximate f at 3.2, I'm between 5.327 and 5.332. So can we use f at 3.2? Can it be equal to that? Can it be equal to 5.331? Yes, it's in between this interval. Can it be f at 333.4? No, it's impossible for it to be that because it's outside of that interval. Okay, so sine, here's our sine Taylor polynomial here. They asked us to plug in 0.5. And this time they want us to have error less than this. So I don't know a bound on the derivative. They just tell me I want my error less than something. So, but the sine is alternating Taylor polynomial. See how it alternates? So the error is no more than the first omitted term. So I need to find the first term that's less than that. And then use the polynomial before that. Okay, so here if I plug them in, I plug in 0.5. Of course we get 0.5. That is not less than 0.0001. So then I plug in 0.5 into the next degree, and we get this, which is 1/3. Oh, 1/8, because I did 1/2. This is 1/2 cubed, which is the same thing as this right here, times 1/6. So that's only 1/18. Definitely less than the value we wanted. So we go to the next one. And here, again, this would be 1/2 to the 5th, 5 factorial. So we're left with this. So 2 to the 5th is 32 times 5 factorial. So it's going to be 32. 5 factorial is 120. This is definitely going to be less than that. So we only keep these guys. And the error would be this. And the error is less than the value we wanted. Okay, so looking at the next piece. This time, they gave us a P3 Taylor polynomial. We don't even know what it is. And we're using it to approximate. Using the information from the graph, here's the graph of y to the 4th. We want to show that this is true. Okay, so sometimes AP is going to write things that are pretty cryptic looking. But this right here says we're using the P3 Taylor polynomial, which means degree 3. This right here tells us we're plugging in x to the 1/4. And this right here is the real value. So what we're finding here is the error. We want to show the error in a P3 Taylor polynomial is less than 1/400. Well, they use the P3 Taylor polynomial to approximate, so we maximize using the 4th term. This is what the 4th term of a Taylor polynomial looks like. Now remember, we're maximizing from where it's centered to where we're evaluated. It's Maclaurin, so we're centered at 0. We're evaluating at 1/4. So between 0 and 1/4 on this graph, what's the biggest it is? 15. So that's what you're going to use for maximizing the error. So 15 over 4 factorial, and again, we're plugging that value in to 4. Same thing here, they want you to find the approximation to this to 4 decimal places. So what they really want us to find is e to the negative 1/2. So we know the Taylor polynomial for e to the x, so let's start there. And if we want to know the approximate using negative 1/2, that just means you're going to plug in x equals negative 1/2. I want 4 decimal place accuracy. So first one, that's not even a decimal place. 1 decimal place. Probably 2 decimal places. And you keep going until it's less than or more than 4 decimal places of accuracy. Cosine x, and they want you to use it to evaluate cosine of pi 12. Here's the exact value using my calculator. So here's my 4th degree Taylor polynomial. That's what they wanted us to use. We're going to plug in pi 12. So I plugged in pi 12ths for the x, and this is my value. So I know if I subtract these two, I get the error, and you can tell how close these are. Now, I don't really need to do Lagrange error here because it's an alternating series. An alternating series is no more than the first omitted term. So my first omitted term would be the 6 derivative over 6 factorial x minus c to the 6. Well, we know that the derivative, oops, I'm sorry, I didn't mean to write that, but this is Lagrange. This is the derivative of sine or cosine is always less than 1. We plugged in pi 12ths, so this is the error using the Lagrange error. We would maximize this on where it's centered to where it's evaluated. We can also use the alternating series error. Now look at, what would the next term in this series be? It would be minus pi 6th over 12 is 6, distributing those, times 6 factorial. Isn't that basically kind of the same thing we got right there? Sometimes they're exactly the same. Sometimes the cosine or sine will actually, making it less than 1 for the derivative makes it a little bit bigger. And same thing here, they just asked, if you approximate it, what values is it going to be between?